Our last bonus problem from section 4.7 is we're going to build a better can. Now, I'm talking about cans like cans of pop. And this one comes courtesy of Courtney, who brought it in last year, because Royal Crown Cola, RC Cola, I always joke is my corporate sponsor, because when we do work with matrices have dimensions that are always given in row by column. So I joke they're my corporate sponsor. In any case, so the last problem is to build a better can. Now, by build a better can, we're being environmentally conscientious. We're trying to minimize the amount of metal that goes into the can. And so the amount of metal that goes into the can is really proportional to the surface area. So that's what we're going to try and minimize, is the amount of surface area for the can, but it still has to have the same volume, right? I mean, if you start selling people cans with less volume, they're going to be kind of unhappy. So let's think on a few things. Well, first of all, the volume of a can. So the volume of a can, we're going to idealize that and call it a cylinder. Volume is going to be area of the base times height. Now, with a 12 fluid ounce can, 12 fluid ounces is approximately 22 cubic inches. So we're going to work in inches. I mean, typically I like to work in metric units, but we don't relate to those very well, so we'll do it in inches. We want to minimize the surface area under this constraint that the volume is 22 cubic inches. That's a little bit more than 12 fluid ounces. It gives you a little bit of room at the top for some air. So, okay. Now, let's see. What else do we know? The surface area. We got to calculate the surface area of this can. So, let's see. Jeff's beer. There we go. All right, so the surface area. How are we going to find the surface area? There's really two parts of the surface area. Yes?
We were talking about RC Cola, now we're talking about Jeff's beer. Can we explain the difference, please?
My beer tastes better. That's the big difference. All right. We'll call it RC beer, okay? There you go. All right, so let's go back to the surface area. The surface area, this is kind of like what we did in the last, or the first part of this video, where we had, a couple different pieces of things, like when we minimized the surface area of a box. There was the area of the sides plus the area of the base. Here, we've got two different components to the surface area. There's our lid, the bottom, the top and bottom of the can. Top and bottom. Plus the area of the side. Now I'm going to let you work on the top and bottom. What expression can I put here for that? Or we can call it X, or we can call it R, doesn't matter what you want to call it. Pi x squared is close. Times 2, because you got a top and a bottom, so times 2. Now, as far as the area of the sides is concerned, I'm going to make this a little bit easier. So, if we were to, flatten this out, if we were to cut this along the side and flatten it out, it would be a rectangle. How do you find the area of a rectangle? Length times width. So this distance is going to be a height, which we don't know. But this distance here is really the distance around the top, which is the circumference. And how do you find the circumference of a circle? 2 pi r. Or in this case, 2 pi x. So our surface area is going to be the area of the sides plus the area of the top and bottom. So 2 pi x times h. Well, we're running into a familiar problem, right? This depends on two variables. It can only depend on one. So, what should I do? Get rid of h. Good. How do I get rid of h? Solve for it. And we can solve for it right here, because the volume is going to be 22. Okay. So the volume is 22. That means that h is 22 over pi r squared. Pi x squared for us. So let's put that in for our surface area. 2 pi x squared plus 2 pi x times 22 over pi x squared. Okay. The nice thing is that this simplifies, and it also depends on one variable. So I'll call that s of x. That's what you're working towards, is a function that just depends on one variable. You can't maximize or minimize functions in this class that depend on more than one variable. So you have to get it down to one variable. Calc 1 is calculus of one variable. So s of x is 2 pi x squared plus 44 over x. Or you could also think of it as 2 pi x squared plus 44 x to the negative first power. Yay. So we've got our picture, and now we've got our function. What comes next? The interval. So let's work on the interval part of this next. Is there a natural restriction for x? Is there a... Yeah, it can't be 0 or negative. That's it. That's about the only restrictions. You can make a very wide can. Of course, it'd be very, very short. Or you can make a very thin can, but it'd be very, very tall. You know, someplace in between has to be a happy medium. But as far as the interval is concerned, 0 to infinity. Okay. So, let's see here. Picture function interval analysis. S of x is 2 pi x squared plus 44 x to the negative first power. What's s prime of x going to equal? 4 pi x minus 44 x to the negative second. Okay. What do I want to do with this? Thank you. Set it equal to 0. We can factor out a 4. I'm probably going to clear up the denominators first. 4 pi minus 44 over x squared equals 0. And I'm taking multiply both sides of this by x squared to clear out the denominator there. And there's an x here as well. So try and clean this up a little bit. X squared. That's going to give me 4 pi x cubed minus 44 equals 0. That's a little friendlier. And you're right, we could factor out the 4, but I'm just going to do it this way. 4 pi x cubed equals 44. X cubed equals 44 over 4 pi, or 11 over pi. So what's x? How do we solve for x? Cube root. So cube root of 11 over pi. Wow, kind of a strange number. Let's get a decimal value on that. So let's see. Under the math menu, cube root of 11 divided by pi, about 1.52 inches. Bless you. We can also check real quickly that this is actually going to be a minimum. We can do that with a second derivative. S double prime of x would be 4 pi plus 88 x to the negative third. And at cube root of 11 over pi, S double prime of cube root of 11 over pi, well, I don't really need to calculate this value. This is positive. 88 divided by something positive is going to be positive. So this is going to be greater than 0. If it's greater than 0, you've got what kind of a shape for your graph? Concave up. And so if the graph is concave up, then your critical points have to be a minimum. So therefore, cube root of pi over, or 11 over pi is a minimum point. Now the interesting thing is, if you actually put this in and figure out what h is, because this is our radius, 11 over pi, h is twice that. And I observed that numerically. I didn't observe it by, some kind of trick of algebra. It's just going to be 2 times the cube root of 11 over pi. I did it when I plugged in to find what h is. So I can show you here. So that's the decimal value for the radius. And if I multiply, you know what? I'm going to store that in x. But if I multiply by 2, I get that number. Let's compare. Now, twice the radius is the diameter. Let's compare the diameter to the height, though. And let's see. Way back here, we got our expression for the height, right? It's 22 divided by pi x squared. So if I take 22 divided by parentheses pi x squared, I get the diameter. So I didn't verify it by some nice tricky algebra. I looked at it one time. I'm like, yeah, it's not worth it. I'm sure that I could verify it directly with some algebra. But really what this is giving you is the dimensions of our new can. Our newly designed can is going to have a diameter and a diameter and a height which are the same. So basically, it's going to look like this. So, I mean, looking at it straight on, what's it look like? It looks like a square, right? Its height and its width are the same. Now, I'll pass it around for you so you can get a kind of compare it. You see its heft. Actually, my old neighbor, who's a World War II veteran, and D-Day is tomorrow. But he's a World War II veteran, and he made this for me. And he swears that it's within 1/10,000th of an inch of accuracy. I don't know. I think he's a little bit off over here, but whatever. Here, let me pass this around. You can give it a good feel. But the problem with making a can like that is severalfold. First of all, you'd have to create new vending machines all over the place. And a bigger part of it is you, the consumer. It doesn't have the right feel. It's not comfortable in your hand. If you put that in your hand, it just feels kind of awkward. So, yeah, it's weird, yeah. But you will see that shape. If you look in the supermarket stores, cans of corn, Fresh Like Corn, has that square-type packaging so that they're trying to minimize the amount of metal that they need to make for those cans. So, what's that? Yeah, condensed milk, similar stuff. Now, like your Red Bull can, those aren't really good dimensions because you're very, very thin but very, very tall. So it's going to require more metal to get the same volume. Yeah. All right, but they do cool stunts too, so we'll cut them a little slack. All right, that's our last one for optimization. Any comments or thoughts on that one? So another really cool visual demonstration, right? All right, good deal. Thank you. Homework. Yes, I do have some homework for you. Oh boy. Yeah. All right. So let me put the homework here. 3 through 9, 13, 19, 21, 23. I have a comma here, which I think means I have more to add. But you got a test next week, so we'll call it a day there.